Hi everyone, welcome back to the post-lab talk. So at this stage you should have completed your lab. You will have watched the pre-lab video, the lab video showing you experimentally what needs to be done. You've done the lab yourselves, you now have your data in hand and you want to put your lab report together. Well, you're going to start by your classic approach to an analytical lab report, your title, aim, introduction, and set out the procedure as you did it, and remember to write it in the proper English way, in the kind of the past perfect tense. This was done. A solution was made, not I made up a solution of, but a solution, a 0.02 molar solution of KMnO4 was made by weighing out blah, and so forth. So you will write that. And then you'll come to you present your data, and this needs to be presented, and again remember you need to have a copy of your own raw data in as a sheet as part of your PDF. So you need to create it as part of your PDF to show that the data for the graph that you've drawn is your own data that you've used in the lab. So you'll have a chart that looks something like this with various absorbance values on it. Molarity, I haven't given them to you. You'll be working those out yourself. And you will have seen how to do that in your in the stoichiometry session that we will be having in tandem with this Beer-Lambert law. And so we will create a graph. Now, we have solutions 1 to 5, which were the solutions that we made up as standard solutions using the serial dilution technique method. And we will also have a final value here of our unknown solution. So without using this, because remember, the first 5 are our standard solutions. They are the solutions and their corresponding absorbance values. They are the data that we are going to use to create the graph that represents the Beer-Lambert law. Remember, I'm going to draw it up here again. Absorbance equals epsilon C D. I'm going to talk you through what all of those mean and why they're important. I did say in the pre-lab video that A is absorbance and C is concentration, but there are 2 other mathematical factors we need to take into account. So initially, all we're interested in for the moment is our absorbance and our concentration, and we'll take the concentration values on the x-axis, on the x-axis, and our absorbance values on the y-axis. And remember, this is our most concentrated solution, so our concentration for this will be the one highest up over here, and solution number 5 is the weakest. That's going to be the one closest to our 0 point. So if you map them or you graph them starting this way, expect your concentrations to be dropping, and they will. Now, okay, so we have a graph, and how do we use it? Well, we have to think about what these 2 other factors here are, okay? Now, A is absorbance and C is concentration, but D is an important factor, because if I say I've got a 1 molar solution, and we look at the concept of the vial that we have with our solution in it, light comes in, passes through, and we detect what comes out, and that allows us to determine what our absorbance is. Well, if I have a 1 molar solution and it's passing through something that width, but I have a 1 molar solution and it's passing through something twice the width or 3 times the width, then even though the concentration is the same, the path that the light has to go through is 3 times as long, and therefore, statistically, will come into contact with 3 times as many molecules. Therefore, 3 times as much light will get absorbed, even though we're only dealing with the same concentration. So D here relates to pathway or distance. Now, luckily, some genius, when they were designing the spectrophotometers, those little vials that you're using, that you put your solution into, that look like this, all have a dimension of 1 centimeter. So D here is always 1 for us, and that makes things quite easy. But it's important to recognize that, we have to take it into account. And we have to know what's going on with it. So that leaves us with this final species. So we don't really need to worry about D, okay? And plus, because we're comparing like with like all the time, because we always are using the same distance or the same pathway, that makes a big difference, okay? In our experiments, the distance of the size of the vial is always the same. What is this? It's called the molar, let me see, I'll write it here. Extinction molar extinction coefficient, and that's written in your lab books, and you can see what that is. So our molar extinction coefficient is this epsilon value here. But what is it? Well, it is the slope of the line. It is the relationship between how the amount of light absorbed is affected by the increase in concentration, which is the slope on our line. So for every change in concentration, what change in absorbance do we expect to see? And if you think about what the slope of a line is mathematically, y2 minus y1 over x2 minus x1, we're looking at the changes in the y value and how they compare to changes in the x values. And here we have absorbance, so we're looking at how much absorbance changes in effective concentration. If absorbance change, the slope of this line will kind of depend. So if when a concentration only increases a tiny bit, we see a huge difference in the amount of light absorbed, then we don't expect our slope to be something like this. If when we increased concentration, we only saw negligible increases in the amount of light absorbed, then we'd have a slope that was much closer to the axis line. So when you create your graph, what you then need to do is determine its slope. Okay, and when you put it into Excel, and you can ask, and you plot your graph, your XY scatter, and you add your trend line, you can ask it to display the equation of the line. And that will be in the form y equals mx plus c, remembering that the number in front of the value x is your slope. M is the slope of the line. So we have y equals mx plus c. So when you create the graph, I said earlier that it's in the pre-lab talk that a very crude way of determining, looking at our final value here, and to determine the concentration, we could just simply read across and down. Okay, so we could, what we call extrapolate, let's give it a bigger history, we could extrapolate from the graph, and that's just reading across and reading down and going, oh yeah, that's our ballpark value there. So the extrapolating from the graph method is not a particularly kind of accurate way mathematically to do it. Once you've created this graph and you determine what the slope of your line is, then we don't need to worry about the graph anymore. Okay, we've gotten what we need from it, which is this value here. So once you've determined the molar extinction coefficient, and we have our equation A equals epsilon C D. Now, if we have a numerical value for this, remember what we'll always want to do is to determine what the concentration of our solution is. I can rearrange this equation here and say C equals A divided by epsilon D. So for my solution down here, for my unknown, and for any KMNO4 solution going forward that I tested in this exact way, well then I could determine my concentration straight away by having my absorbance value, which you get by sticking your value into the machine, by sticking your sample into the machine and reading the absorbance. D is always 1 in our case, because the vials, we use the pathway or the distance that the light has to pass through is 1 centimeter, so D is 1. And this value here we have from the slope of our graph. So in this experiment, by creating the calibration curve, you have given yourself a tool by which you can then go forward to determine the concentration of any KMNO4 solution made up in the same way but with different values, by simply putting your sample in, taking an absorbance value reading, dividing that absorbance by epsilon multiplied by 1, okay, which is just your molar extinction coefficient, which is the slope of your line. And from then on, this here is now a mathematical tool that you've created by taking serial dilution, creating a number of solutions, getting corresponding absorbance values at the lambda max wavelength, comparing how the concentration kind of relates to absorbance by creating a line, a linear graph, finding the slope of that line, epsilon. That is now the tool you've created to determine. So the overall aim in this experiment was to determine the unknown concentration of a known solution using the Beer-Lambert law. But there are other aims. The other aim is to learn how to use serial dilutions, to learn how to understand the Beer-Lambert equation, and also to follow on with the questions that are in your lab report. So very quickly before I finish, let me just say this. Your lab reports need to be written up in the classic style Professor Lowry has asked, that they're delivered aim, title, aim, introduction, a little bit of introduction. Remember, keep your aim kind of short and sweet, just two, 3 sentences. A little bit of introduction on what you understand the Beer-Lambert law to be. Procedure, okay, how you made up your solutions, written in the correct way. So such and such was done, a solution was made, the absorbance was read by the spectrophotometer, and so forth. The data was collated. A graph was created, and its slope was determined, and so forth. Okay. Then so after that, then your results need to be presented. You need to present your results in a raw format like this, ensuring do not leave the lab without a signature on the bottom of your data. Okay, and remember that data is the data that needs to be included in your graph that goes in with your report. Okay, if it doesn't, there's something fishy looking going on, and we'll consider it some sort of plagiarism. So your report, and then the final questions. Okay, a little bit of a conclusion, how successful your experiment was. Now, one of the things you should be looking out for in the conclusions could be, where did I put my chalk? So if, for example, when you create your graph, all your points are sitting beautifully on the graph, happy days. The reality is that's not going to happen, okay? So what you'll find is that there'll be some sort of deviation, from the graph. That's a human error sign, okay? That's a sign that when diluting down, you didn't dilute properly, there was slight changes. These are going to be very small and very low concentrations of solutions. So any slight deviation, even any slight kind of hiccup in how you make up your solution will make a difference to how accurate that is. So, you can point out human error. That's perfectly acceptable. It doesn't mean you failed the lab. It means you recognize that these aren't sitting ideally on the line. That doing it over again, maybe you could pay a bit more attention or whatever to how you were doing it. But do watch, if you're not sure of how to do this going forward into other labs, do make sure you concentrate on watching the lab as it has been performed by the technicians in the videos that we're posting for you going forward. Best of luck.